It is recording. Yeah. Okay, so we have our script. Now we have our runoff volumes. We have all the different associated land types in relation to that. So now we want to start to visualize that. As mentioned before, we're going to envision what the drainage volume for each one of these areas looks like. So the first thing we want to do is combine our volumes all together. So you can see that all those different land cover, vegetation, slope conditions are generating these different volumes. So we would need to add those all together for each one of these drainage areas. So here's the first drainage area, here's the second. So we're just going to focus on this first area. So we're going to go to our mass addition. I'm just going to start dragging these into there. And if you hold shift on your keyboard, that'll allow you to add multiple lines to this. If you don't hold shift, it'll just replace them. So make sure to hold shift. You'll see that green plus sign show up. Oops. Zoom. Okay. So we have this. I'm going to copy one of these just to see what our total runoff volume is. And go ahead and flatten this so they're all combined. Oops, let's not do it there. Let's do it on this side. So we've got a total of 339 cubic feet of runoff. These values, or this value is independent or dependent, sorry, on my rainfall slider. I'm going to be changing this around. So I'm going to go ahead and just copy this information as a separate independent panel. So I'm just going to type 339. And I'm going to relabel this as our 1 hour, 2 year rain events. So that's how much volume is generated from a 1 hour, 2 year rain event. That's that 0.2 factor within this drainage area. I also want to see what it looks like. So let's move forward from here. So we have our volume. As mentioned before, we need to visualize what that actual impact is on the site. So what we can do is reference this drainage area into Rhino now. So parameters, surface, set one surface, and turn that off. I'm going to go ahead and use the project to C plane. So project an object onto a plane. So now we have just this nice flat area of that drainage area. And so now what I'm going to do is do a little intersection operation where these two geometries are going to overlap or intersect, and the leftover piece that intersects is going to give us a geometry that we can determine the volume from. So I'm going to go ahead and do extrude now. So extrude, just the simple one, not any of these additional ones. We need to extrude this in the Z direction. So I'm going to type Z for unit Z, drag this into there. Now I'm going to create a number slider. I'm going to start off with 0.25 less than 4. I guarantee it's not going to have to go above that in order to intersect. So now you can see that as I extrude, we start to see how runoff volume would begin to overlap on top of that terrain. So this is still just giving us an entire extrusion of that. It's not actually giving us the separate geometry. So this is where we do part of the intersection operation. So I'm going to go to intersection tab, shape. I'm going to use solid difference. And the way this is going to work is that you're going to use, I'm going to turn this off. Your extrusion part is going to be into this A component, and then you're intersecting it with this surface. So that's what's showing already. So I'm going to grab it into there. And so now you're left with just that kind of space that goes above that surface. And what's nice is that now I have more or less a representation of that volume. We need to see if that's anywhere near 339 cubic feet of runoff. So we can double click, type volume, find our component, drag that into there. I'll turn this off. Grab one of these panels again, and the volume shows that this is in fact nearly 1,500 cubic feet of runoff. So that's nowhere near this amount. So we're gonna, let's just shift this over so we can kind of see it a little better. So the idea is that we want this volume to be close to this. So I'm gonna just start dragging my slider down. It still gets close to 339. Remember, it's okay to exaggerate a little. I'm going to drop that to maybe 1 point. Let's see what 1.19 does. Nope. That's pretty close. That's a little bit less, but I always like to overestimate, especially when it comes to runoff volume. Okay, so there you go. So now you have a representation of that volume for a 1 hour, 2 year rain event. Again, the idea is that you want to show multiple rain events and how much they would impact the site. So what's nice is that I can go back to my rain event slider. If I take a second here, and again, I sent this all to you guys just recently, or I will. I don't know if I did actually send it yet. Did it not save in here? Oh, it's a little bit further into this. So there's where I get that 0.52 value. Let's see what happens when I look at a 5-year rain event as well as a 25-year rain event. Obviously, you can do a whole range of that. So the other slider, so let's drag this to, what was that other value? 0.89, all right. And so now our runoff volume is 580, so I can just copy and paste this, change this to a 5-year rain event, and change this to 580. Then the last one was 1.5. So that's already good. That's from a 25-year rain event. That volume is 978. Okay, so what's nice is then I can add some sliders to this input in order to create those volumes as well. So let's go ahead and just copy and paste this. Again, I'm just going to add it to this slider, and so we'll have 2 now. But I'm going to drag this one up until it gets close to 580. This is going to be a pain, isn't it? That's good. 588, not bad. And so then one last one. 978. Ooh, close, 974. That's good. Like I said, it's always good to kind of overestimate. So now you can see that there are, in fact, 3 different areas depicting those different rain events. I believe the assignment only asks for you guys to do 1 rain event, but in order to earn that's really just the bare minimum. So I would highly recommend looking at a series of different rain events just so we understand the volume change with those different rain events. One last thing. So again, it's all about the visualization of this. So, I mean, sometimes water's red. If there's a lot of metals in the water, it can come off as kind of rustic looking, but I like to keep my water looking a little more blue. So let's go ahead and do that as well. I mean, you don't have to because this isn't the way you're going to produce your drawings, but again, visually it'll make it look a little better. So I'm going to do custom preview. Let's turn that off and let's create a swatch. And I'm just going to give it a nice blue hue. And then what's nice if I give it some opacity. Some areas overlap, which make it appear a little bit darker versus the other one starts to fade out a little. Again, it'll look better in Illustrator because you can't actually bring this solid geometry into Illustrator, but in Rhino it does the trick. So there you go. So here's 3 different rain events. Labeling these would be important in the actual Illustrator portion of this, so we understand, again, what that rainfall intensity is that's contributing to this. So the next phase is, again, to then look at what parts of this drainage area are having the largest impact or influence on this runoff volume. What's nice is because we have a lot of that information already kind of sorted out by all those different parcels, we can do just that. So what you're going to do is go back to the script, go to parameters, and we're just going to group them all together by holding again the shift key and inserting them all into here. And this is important to do it in the same order of operation. So I'm just starting from the bottom or from the top to the bottom. So there's my 4 different conditions. I'll turn this off. I'll go ahead and flatten this at the start. So now we just have 11 reference surfaces in this case. You guys will probably have a different value, but that's okay. And then the next thing we need to do is also group our volumes together. So I'm going to go up to primitive and do the number component. I'm going to do the same thing. I'm going to start at this top and move down to grab these. And I'm going to do the same thing. I'm going to flatten these values. And now because I've sorted them in the same order, I have my reference surfaces and their corresponding runoff volumes. So you can see that there's some that get as little as 7.29 all the way up to 216 or even 329. So there's quite a drastic difference. It's not that they're all equally contributing to this runoff volume. And a lot of people may think that, well, you have some areas that are fairly large, like there's a pretty big swatch, there's another big swatch. It's probably common knowledge that the larger the square footage, the higher runoff volume it contributes to, right? That's not always the case, which this part will reveal. I already kind of know the answer to this because I've gone through it. So let's go ahead and see if that logic is accurate. So again, this is where we can be a little more creative in the visualization aspect, because it's really just visualizing data. It's not so much of being completely literal with that representation. That's what this part's doing, but we do want to see which areas are directly contributing to that. I'll show you two different techniques since it looks like we have plenty of time. So one logic is to just color code each one of these regions based off of its volume. So what we can do is take this number component, go to math, do a bounds. We can deconstruct this bound. This is a lot like this is going to be a lot like the slope portion we did. So I'm going to drag these numbers into this value. I'm going to have the start and the end. And this is essentially going to give me a color coding based off of that runoff volume. Yeah. I think this should work. So I'm going to, again, give this maybe more of a blue hue. Maybe we have it kind of dark to really represent those higher areas. And then maybe it's just a slider. More of a baby blue hue. So the idea is with the sliders that it's going to show which areas are contributing the most to this runoff volume, where the darker blue is generating more volume versus the other areas. So I'll do again, custom preview. Any guesses before I reveal which area you guys think is going to contribute the most to this runoff?
Gotta do that bottom one.
This one? No, we have like 11 different segments of land.
I think I misunderstood your question, but which one's going to contribute is going to be that hill.
Maybe. Or we'll see, right? I mean, it's the soil type you're going to find out is probably going to contribute the most to that. So, drum roll, please. Let's go ahead and let's turn on something that's not important. Let's just do something even easier. This area appears to be contributing the most to that.
That's cool.
So you can see that it's pretty flat in relative comparison to the rest. But I can tell you for one thing that the soil type and the vegetation cover are what's ultimately determining a lot of that runoff volume. That's because I believe it is within the clay soil type, so that has a high coefficient value, as well as it being in the grass. So it makes sense that grass captures less runoff than trees, or intercepts less, as well as you're comparing sandy loam, which has one of the highest percolation or infiltration rates, versus clay. So when you combine that together, you start to see that square footage, slope aren't always going to have the biggest impact. A lot has to do with that land cover, and this is what's nice, is that this can start to showcase this. So moving forward, or what will be expected later on in the semester is that you'll be able to determine where that area is located and come up with some kind of solution as to how you can resolve some of those potential problems of runoff being contributed. Your assignment will also the other assignment will also deal with more of urbanized factors. So the difference between what asphalt can do versus permeable pavers, those kind of things as well, not only just natural conditions. So this is one way to start to understand that condition. I believe the second lightest or the second darkest blue is also grass, but I think that is also in the sandy loam. So it's amazing what trees or forested areas can do, right? We're all landscape architects. We kind of inherently know that, but now you have the tools to show the evidence for that. Okay, so again, this is a fairly simple visualization technique. Let's look at another way that you can also do that. You can go ahead and turn that part back on. And what we're going to do now is something a little more interesting, I suppose. So let's go ahead and find the area of each one of these surfaces. So again, this is giving us the square footage. The reason I want to do that is for this part of the operation. And I'll just delete this. I don't really need it anymore. So what we'll do is go to our vectors and populate each one of these surfaces with a series of random points. So we have, what this needs is the geometry that's going to populate. That's all those different 11 surfaces. There's a number of points to add. I don't want to give them all an equal amount. I want to give them essentially a point for every square footage. So we're going to find out that or calculate that. So by looking at the area, I want to have a point for every 50 square feet. So I'm going to go to math. I'm going to divide the area by 50. So this is essentially going to give me, again, a point for every 50 square feet in that area. So I'll drag that into there, to my numbers, and then drag this into there. So like I said, now I have a nice equal distribution of random points on this. Imagine this could be symbolic of rainfall droplets or moments in which the water or rain is falling on the surface. You can make that density of points a little bit more or less, depending maybe on just your computer's capabilities. So I'll just drag that back up to 50. 50 is a good number for this one. So what I'm going to do is, with each one of these points, I'm going to create a curve or a circle. Let's go ahead and graft or unflatten this actually. It's not going to make a difference. You'll see it's still the same thing. Yeah. So now I'm going to go to curve. I'm going to do primitive and do a circle. Now I have, if I turn this off, just a bunch of circles all over. But we want the radius of each one of these circles to, again, correspond with the runoff volume of those areas. So that's what these come into play. You'll see, so these circles have a radius of 1, which look fairly decent on this. These numbers are way more than 1. So if I were to just directly insert that into there, you'd have circles with a radius of 329 feet. Probably not what you want to have visually shown. So we have to adjust these values or remap them in this case. So I can go to Math and choose the remap numbers. I'm going to go ahead and drag that into there. I need to find the start and stop values. So that's our min and max. That gives us our bounds. And then I need to essentially say, okay, take those values and adjust them to something different in a linear fashion. So if I just test this a little, if I drag a 4 into there, that's a little much. If I were to imagine there being some at 4, 3 might work a little better. So I'm going to go ahead and construct a domain for this value. And I'm going to say I want the smallest circle to be 0.5, or wherever those areas are or that are 7 cubic feet, they're going to be represented by those circles. I'm going to say 3 to be the largest here. So now I'm going to go ahead and graft this input, drag it into there. Now you can see that their circles adjust size based off of those corresponding areas. So again, you remember this area had the highest, this one was the second. So these circles have a radius corresponding to those same values. So what's nice is that you can then give them a fill or convert them to a surface. And again, just because visualization relies on multiple factors to be changing, so we have size. Another ideal one would be color. So let's go ahead and you could take it a step further and actually extrude these up like vertically based off of that volume as well. That's kind of up to you. If you do extrude, Z, go ahead and graph that as well. So now you can see again these ones also go up higher than those other ones. It's okay. I'm not a huge fan of it. I don't buy it too much. So I'm just going to go ahead and remove that, and I'm just going to move them all an equal distance. If I hit Z, it'll just default it to 1 unit. That looks a little better, so there's no overlapping with that other surface. Again, what's nice, I can give them that same kind of color coding logic. So I'm going to grab this color gradient, deconstruct this bound value. So I have my numbers, which are going to go into here. The start's going to go over here, the send over there. Again, maybe give it a blue hue, or you can get more into color theory and use a complementary color such as orange. Let's go ahead and do that. Custom preview again. And let's go ahead and graph to that. So there you go. So again, it's a way to kind of indicate which areas contribute the most to the runoff volume versus others. I'm not saying that this is the one and only way to do it or that you have to do it this way. It's just providing a little bit more information to the site so we understand why these volumes are being generated. And obviously do that to this site. Yeah. I'll go ahead and stop this now.